Hello, my babies. Welcome to your snow day physics. I just couldn't do it. I just couldn't let this many days go by without some physics for you. So if you recall, last Thursday, we were talking about pendulums and sort of just introducing a mass on a spring. And this mass is following the laws of simple harmonic motion. There's tons of examples of this in nature. We're just going to deal with a couple today. I'm going to demonstrate this, and then also we're going to see a pendulum and look at the relationships between forces, masses, acceleration, energy, velocity, all kinds of great stuff. But for right now, I want you to watch this mass on a spring. It's in equilibrium, and if we took this out into space, we could actually turn it sideways, and that's the way I'm going to draw it, so that you won't even have to worry about gravity. But a mass bouncing up and down on a spring follows the same patterns that a pendulum swinging back and forth will follow. And so we could time the period of this mass, and it would be for one cycle, the time from the equilibrium position to the maximum stretch point, back to equilibrium, maximum compression, and then back again. Now I know that seems like a lot, but it's basically, watch, I'm going to follow it now, from here, here, here. That's one. Here, here, here. That's another one. Here, 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 and obviously you would still count. So it's a full cycle just like in a pendulum. All right, I'm going to jump out of the screen, and then we're going to take some notes. We're going to look at different characteristics. There's a whole bunch of great physics involved here. All right. Back to the notes. There we go. That looks normal. So, simple harmonic motion. There are a lot of characteristics. First of all, the period, so the time it takes to go from one position all the way through a full cycle and back to that position again, is 2 pi. And if you don't know what pi is, get out of my class right now. Times the square root of the mass divided by k, which stands for the spring constant. If you recall, we did this with pendula last Thursday, and it was the period equals 2 pi times the length of the pendulum over gravity. So that similar equation shows up on purpose. Now we can also look at a whole bunch of different characteristics, and so we're going to create a table. And those characteristics are going to be force, acceleration, potential energy, elastic potential energy, kinetic energy, and velocity. And those characteristics are going to change depending on where we are in the simple harmonic motion, okay? So I'm going to draw my mass on a spring right up here, and now we're going to be in a 0G environment. So out in space, there's our little spring, and there's the mass. If this represents equilibrium, and if I stretch it some distance x, that spot is going to be at max. Okay? Remember, that same x value exists over here on this side. I'll draw it in. And that's the distance that it compresses. So this is our mass, m, in its equilibrium position. That means there's no force, it's just relaxed. If I stretch it, I apply a force. If I compress it, I apply a force. And they're the same. And so in our table, I'm going to put, what will it look like if it's at the maximum stretch or compression versus at the equilibrium position. There's going to be a whole bunch of zeros in this table, and I think that's where it's going to be easiest to understand if we think about the kinematics. So imagine that this is moving back and forth. We pull it, it's at rest, at its maximum stretch. We release it, and it just goes back and forth, back and forth, back and forth. It stops here, speeds up, speeds up, speeds up, woo! Flying at the equilibrium spot, slows down, slows down, slows down, stops again, speeds up, woo! Flying through the equilibrium position, slows down, and stops, and it just completes that over and over again. So the place where it was hardest to pull, the maximum force spot, would be at this maximum X value. And the force to pull or push or compress or stretch a spring is just K times X. At the equilibrium spot, that's where it's going to be flying past. That's the fastest spot, but it's also zero force because that's where the spring is actually relaxed. If we go on and we use this as a basis for figuring out all the rest of it, it's really not too bad. Here we're going to use Newton's second law. So if, I'll do this over here, if F equals ma, and at the maximum stretch or compression spot, F equals kx, and if I solve for acceleration, well, bam, I get kx over m. At the equilibrium spot, there's no force pulling or pushing the mass, and so again, if force is zero, acceleration has to be zero. For potential energy due to a spring, if you remember from when we did kinematics, that's just going to be 1/2 kx squared. At the equilibrium spot, there's no stretch for the spring, so that's going to be 0. For kinetic energy, that's where it's cruising the fastest, and so its fast spot is at the equilibrium position. That means that all of the elastic potential energy that existed here got converted to kinetic energy here. So we're going to put 1/2 mv squared for the equilibrium spot, that's the fast spot, but at maximum, it's going to be 0. And the reason for that is, at maximum, that's where it stops. So we pull it, it stops, we release it, speeds up. It's all kinetic right here in the middle, slows down, stops again, 0 kinetic, maximum potential. So these two, of course, are going to go back and forth between the maximum stretch and the equilibrium spot. The velocity is actually calculated using these two equations together. So the velocity is 0 at these maximum stretch spots, so we can put that there. And that should make sense. The kinetic energy is 0, the velocity is 0. But for potential versus kinetic here, I'm going to use these two equations. We'll write them over here, and then we're actually going to solve for velocity. So the potential energy at the maximum spot turns into kinetic energy. I'm going to fill in the equations. 1/2 kx squared turns into 1/2 mv squared. The 1/2s go bye-bye. We're going to solve for velocity. So we'll divide by mass and then square root everything. So the velocity will equal the square root of kx squared over m. And that's going to go right here. Kx squared over m. Square root. So now you can find any of these quantities for an object that is moving back and forth on a spring due to simple harmonic motion. It gets a little more complicated, however, if we want to try to fill in at an x prime value that is not maximum x.